And we are live. Yes, we are indeed live. So, new day, new same code. So, we're doing the lighting. We did the ambient. Right now, we did the ambient. What we are missing is the diffuse component of the lighting. Basic lighting. So the diffuse lighting. Ambient lighting by itself doesn't produce the most interesting results. Okay, so we did the normals. Okay, calculating the diffuse color. So before doing this, allow me to go to Lightcasters for a bit, because this is a tutorial, but obviously I don't really care about the tutorialing part. So Lightcasters, what we want, what do we need right now? So all the lighting we've used so far came from a single source, that is a single point in space. Okay, it gives good results, but in the real world we have several types of light that each act different. A light source that casts light upon objects is called a lightcaster. In this chapter we'll discuss several different types of lightcasters. Learning to simulate different light sources is yet another tool in your toolbox to further enrich your environments. So the idea is that there are here represented three types of lightcasters: directional light, point lights, and spotlight. Okay, like a flashlight or something like that. We don't care about spotlights for now. We don't care about point lights for now. What I want is to simulate like the lighting given by the sun or by the, I don't know, the moon, or whatever, like something like that. So what we want is a directional light. When a light source is far away, the light rays coming from the light like the sun, the stars, the moon, whatever, the light source okay, so when a light source is far away, the light rays coming from the light source are close to parallel to each other. It looks like all the light rays are coming from the same direction, regardless of where the object and or the viewer is. When a light source is modeled to be infinitely far away, it is called a directional light, since all its light rays have the same direction. It is independent of the location of the light source. A fine example of a directional light source is the sun, as we know it. The sun is not infinitely far away from us, but it is so far away that we can perceive it as being infinitely far away in the lighting calculations. All the light rays from the sun are then modeled as parallel light rays, as we can see in the following image. Okay, because all the light rays are parallel, it does not matter how each object relates to the light source position, since the light direction remains the same for each object in the scene. So we don't care about the light position. Because the light's direction vector stays the same, the lighting calculations will be similar for each object in the scene. Perfect. That's basically what I wanted to say. So now, how do we calculate the diffuse component of our directional light? Yep. Now, we need, obviously, here we have the light position. The position doesn't matter to us, so we know that what we want is the float 3 directional directional light light direction directional, so sun light direction, or directional light direction, oh my god, and the direction light color. Float pad, so we have, because they need to be like 16 bytes aligned or something like that. Okay. HLSLC buffer. Packs data into 4 byte boundaries. Okay, so they need the 4 bytes alignment basically. So packing rules dictate how tightly data can be arranged when it is stored. HLSL implements packing rules for VS output data. Okay. HLSL packing rules are similar to performing a PragmaPack 4 with Visual Studio, which packs data into 4 byte boundaries. Additionally, HLSL packs data so that it does not cross a 16 byte boundary. Variables are packed into a given 4-component vector until the variable will straddle a 4-vector boundary. The next variables will be bounced to the next 4-component vector. Each structure forces the next variable to start on the next 4-component vector. This sometimes generates padding for arrays of structures. The resulting size of any structure will always be evenly divisible by size of 4-component vector. Arrays are not packed in HLSL by default. Okay. So here a float is 32 bits, which is 4 bytes. 4, 8, 12, 16. So this is a vector. Here it starts a new vector, and here it stays in the same vector. Here 2 vectors starts a new vector, so you need to basically pad. Here some padding is inserted. Okay. Here vector, here vector, and then at the end you have two other bytes of padding. Here is a single vector. Here 1, 2, 1 is a single vector. Here 1, 2, 3 padding, new vector. Okay. Here is a single vector. Here is a single vector. Here is a vector, and then a new vector starts. So basically other 8 bytes of padding here. So 2 floats basically. Okay, so just to be clear, you have these are 16 bytes. These are if I were to do this, okay, there is like an implicit padding here because this is 16 bytes. This it's 12 bytes, and then you have 12 bytes. So since each variable, each member of the buffer has to start at the 16 each variable, if it doesn't fit in the current vector, is basically pushed down, okay, using padding, so that it fits in the next vector unit, basically, or something like that. Variables are packed into a given 4-component vector until the variable will straddle a 4-vector boundary. The next variables will be bounced to the next 4-component vector. Okay, that's it. So here it fits, here it fits, and the vector is over. Here it fits, here it doesn't fit, so you have to add the padding. Okay, then this fits, and this is 4 bytes. Sorry, these are 16 bytes. These are 16 bytes, and these you also have another, because each structure forces the next variable to start on the 4-component vector. This sometimes generates padding. The resulting size of any structure will always be evenly divisible by the size of the 4-component vector. So basically you also have padding here, okay? Because they're split into this vector, to these vectors. 4-component variables are packed into a 4-component vector. So this thing right here is packed into a 4-component vector. You have here 3 components. The 4th component is basically padding. Okay. So light constants, fantastic. We have to no. Here it is. No. Here it is. The float 3 gets renamed to vector 3. Fantastic. So that's the thingy. And in color I'm doing strength, direction, light, color. Can't I just call it sun direction? I don't know. Whatever. Direction, light, color. If we do this, something will break. Whoops. Let's do a rebuild. If we do this, everything looks fine, of course, but we need to provide constants, the ambient color and the strength, the padding will be ignored, direction light direction, and the directional light color. I don't like it. I deeply dislike it. So sun direction, sun color, and here it's sun direction, sun color, sun rays direction, sun rays. Is it spelled right? Sun rays. Yeah. Sun rays. So sun color, sun rays direction, sun color. Ambient strength, sun rays direction, sun color. Okay. Sun rays direction, sun color, sun rays direction, sun color. Fantastic. we can go to delete pixel shader and do our magic. So compute ambient light, compute diffuse light, some diffuse light. How? Well, very simple. We take the last thing we need is the actual fragment's position. So we now have the normal vector for each vertex, but we still need the light's position vector and the fragment's position vector. Okay. Since the light's position is a single static variable, we can declare it as a uniform. In our case is the light direction, is the sun rays direction. And then update the uniform in the render loop. Okay. Then the last thing we need is the fragment's position. We are going to do all the lighting calculations in world space. So we want a vertex position that is in world space first. We can accomplish this by multiplying the vertex position attribute with the model matrix only. To transform it to world space coordinates. This can easily be accomplished in the vertex shader, so let's declare an output variable and calculate its world space coordinates. So here we need the vertex shader output. We have the position, the normal, the UV, float 3, the world space, so we want the position in world space. That's it. Normal, the position in world space, the normal, and the UV. This is the position in the projection space. How is it called? It's projection matrix, or it's called clip space. Fantastic. So This is the position clip space basically. Okay, so the vertex shader output, this is the position in clip space. Position clip space, position word space, the vertex shader input is the same, position normal UV. The vertex shader output, it's the position clip space, the position word space, the normal, and the UV. Okay, now monkey. I was like entranced. I was enchanted by the monkey. No. Okay, so the last thing we need is a fragments position. We do everything in word space, so we need the position of word space. So basically the position in word space, I just multiply the model matrix with the position as it is. That's it. And lastly, add the corresponding input variable. Okay, the variable will be interpolated from the 3 word position vectors of the triangle to form the frag position vector, that is the fragment word position. It is the per fragment word position, of course. We obtain it by interpolating the different word positions of the vertices. Now that all the required variables are set, we can start the lighting calculations. The first thing we need to calculate is the direction vector between the light source and the fragment's position. So the first thing we need to calculate is the direction vector between the light source and the fragment's position. So float 3 sun light and we do float 3 opposite sun ray direction, opposite sun ray direction, and this is just minus the sun rays direction. Okay, then we normalize So the unit is the direction vector between the light source and the fragment's position. From the previous section we know that the light's direction vector is the difference vector between the light's position vector and the fragment's position vector. As you may remember from the transformations chapter, we can easily calculate this difference by subtracting both vectors from each other. We also want to make sure all the relevant vectors end up as unit vectors, so we normalize both the normal and the resulting direction vector. So the opposite sun rays direction opposite like direction, normal, we compute now we need to calculate. So as we stated yesterday, we need normal, we need unit vectors, okay. the resulting, so we need to calculate the diffuse impact of the light on the current fragment by taking the dot product between the normal and the light direction, so the opposite light direction. So float diffuse impact, it's just the dot between opposite light direction and normal. Okay. If the angle between both vectors is greater than 90 degrees, then the result of the dot product will actually become negative, and we end up with a negative diffuse impact and thus a negative diffuse component. For that reason we use the max function that returns the highest of both parameters to make sure that the diffuse component and thus the colors never become negative. So we need a max here. Then the float 3 diffuse light, sunlight, the sunlight, it's just the diffuse impact times the sun color. That's it basically. Lighting for negative colors is not really defined, so it's best to stay away from that unless you're one of those eccentric artists. Okay. Now that we have both an ambient and a diffuse component, we add both colors to each other and then multiply the result with the color of the object to get the resulting fragment's output color. So we basically add both components. This is the object color, the perceived color is the ambient light. Sun diffuse light. We add to it the sun diffuse light and then we multiply it by the object color to get the perceived color, and then we return the perceived color. That's it. You can see that with diffuse lighting the cube starts to look okay. Okay, let's try it. Oh my god, that's beautiful. That's actually way more interesting now. What happens if we change the sun? Let's just pretend that we don't get any ambient. So here it's not lit. Okay, here it's lit. You can see like you can see very well. Yeah, fantastic. If you change the light, the sun color, you can make it yellowish. We can also change, like if it is like 0, x, y, z, x, it's 0, then it just points like this downwards, so you can see like something like that. Okay, I can make it to point obviously like this, nothing happens, x, y, z, and not +1. You can see here the light is going like that. Okay, so it's we are lighting all of these. Okay, if we were to do it like this, it would light the face. Okay, if we were to do it like this, it would light the bottom. Very creepy, because it's the Y. If we do it like that, then it's lighting our monkey. The sun light is exactly like this. And if we do it like this, we can see that the sunlight does this, or better for you it's not this but this. Yeah, but that's the same. It comes from the right, so it lights this part of the face, but it doesn't light this part of the face. If we negate it, ooh, what is happening? What happened? I probably like that's okay. Let's see. 0, 0. This is 5, 5, 5. Okay, fantastic. I probably touched something like that, modified some value and destroyed everything. So right here, if we do this, obviously the light comes from here, and thus it lights that part of the face of our monkey, but not the other side of the face. Like this, the light is coming basically from the so we have the minus, so we have minus, so we have x, y, z, we have the minus, so the light direction is something like that, and in fact it comes basically like this, okay, towards the origin. Yeah, it makes a lot of sense actually. Okay, we implemented our direction light. We got there is this part about normals that we will talk about later, and also Blender, like file open, oops, well, okay. Okay. Oh, of course. Blender, blend normals. Object shade smooth, shade flat. Object. Shade smooth. Oh my god, that's fantastic. I want to try, so exporting file, export obj, selected only, no material, the UV coordinates, the normal, strangulate the mesh, assets, not assets, current working directory, meshes, monkey, let's export it, let's go here, do this, oh, flat monkey, like, not flat, smooth, here is our smooth monkey, oh my god, that's so cool, that's so cool, yeah. Smooth monkey. Okay, fantastic. So it works. It also works also with smoother like normals. Yeah, it doesn't look that bad. It's way better than the flat. Okay. Okay. Bye bye. See you like the next time.